Hello, this is the third video about SaLinA, and I will show you in this video how we can implement a complete reinforcement learning algorithm, so A2C, by using SaLinA, and you will see that it's quite simple. Okay, so let me start with a simple code. So here, sorry, but I have all this import I need for my implementation. Then I have this run A2C function that I will run to execute the A2C algorithm. And then I have this main function that is the entry point of my script. Note that this main function I am using the spawn mode, the spawn multiprocessing mode, which is useful when playing with multiple GPUs or multiple CPUs with environments like Mujoko, for instance. And then I am making use of Hydra to choose the hyperparameter of the algorithm. So the hyperparameters are defined in this main.yaml file. I can show you the file. It's very simple. It's just a set of values. So the environment seed, the number of environment I want to execute in my batch of environments, the number of time step I will get at each epoch, the number of epoch, etc., etc. Okay. So first, what I have to do is to define the different agents I want to have in my algorithm. So remember that in A2C, the policy is basically computing actions, and the critic is computing some values. So I will define a first agent, which is, let's say, the P agent, and this agent will compute probabilities for all the different possible actions. In my example, I am making use of the cartpol gym environment. So in cartpol, the input size is the size of the observation is 4, and I can choose between two actions. So I will use as a model just a simple neural network, which is a multi-layer perceptron with one hidden layer of size 32 and 10 activation function. Okay. Of course, you can use whatever you want. This agent will be executed at each time step, and then at each time step, what it will do is get an observation from the environment, and I will tell you more about this later, and then you will compute some probabilities. So the observation, we assume here that they are already in the workspace. So the observation at time t, sorry, it's a get, not a set. From this observation, I can compute some scores. From these scores, I can compute some probabilities. And then I can write these probabilities at time t into the workspace. Okay. So again, my P agent is reading observation, computing probabilities, and writing these probabilities into the workspace. Then, based on these probabilities, I want to decide which action to take. So I have the action agent, which is also an agent. Okay. This agent will also act at time t in the workspace, and then maybe this agent can be used in a stochastic mode or deterministic mode. I mean, when you have a probability, you can choose the action by sampling over this probability, or you can take the max of the probabilities to choose the action. So here we decide that it will be specified through this stochastic argument. So first of all, I will get from the workspace the value of the probabilities. Then, if I am in stochastic mode, the action will be sampled. Torch distributions categorical of probes dot sample. So here just the sampling. Then I will write action at time t. And if it's not in stochastic mode, I mean if it's in deterministic mode, I can just compute the max over dimension 1, so the argmax, and then I can do exactly the same, which is to write the action at time t. Okay, so I have two agents, one computing probabilities and one sampling agent, and then I need a third agent, which is a critic agent. Let me do a copy paste of this guy. So the critic agent is just computing one value for each state of the MDP. So it will work by getting the observation, computing a critic value, okay, and then writing this critic value. And then I don't need the last dimension, so I can squeeze the last dimension, okay, like this. Okay, so I have three agents acting at time t, and these agents are making use of one observation and computing three variables: probability, action, and critic. Okay. One question is about who is responsible of writing this observation into the workspace. In Torch agent, everything is an agent. It means that an environment is also an agent. It means that these variables will be written in the workspace by an agent that is the environment, so that is carpol. So I need to create an agent able to write this type of variables. And we provide already such an agent in SaLinA. So let me first create a function to create a gym environment. So I will create carpol and I will limit the number of episode steps in this carpol. Given such a function, what I can do is create an environment agent, which is an auto-reset gym agent. So auto-reset, it means that at the end of each episode, the gym environment will be reset and a new episode will start again. And to create such an agent, what I need is the function to create the environment. What I need also is the value of the argument of this function. So here I make env with 100 maximum steps. Okay, and then since SaLinA is always working with batch of environments, then I need to specify how many environments I want this agent to capture. So for instance, it will be just, let's say, 4 environment. Okay. This environment agent, what it is doing is that it will read in the workspace action at time t-1, and what it will do is that it will write different variables in the workspace. So the observation, the reward, done, initial state, the time step of the episode and also the cumulated reward. Okay, this is the way we have defined this agent in SaLinA. Okay, so I have one agent which is writing all these variables, and then I have some other agents reading the observation and writing probes, actions, and critique. Okay, so the first agent I can define here is what I will call the acquisition agent. So first I have my probability agent, is it P agent? I have my action agent, which is an action agent. I have my critique agent, which is a critique agent. And when I want to get a new trajectory, what I have to do is to combine my environment agent that will be executed first with my P agent that will then compute probabilities with my action agent that will then compute actions. Okay? Not that if I want to get new trajectories, I don't need to compute the critique values, because the critique values will be used when computing the loss function, but not when just getting a new trajectory. Then I want to execute this guy over multiple time steps, so I will encapsulate this guy into a temporal agent. Okay. And now, just to show you, if I have a workspace, I can execute my acquisition agent over this workspace for instance, 32 steps, and in stochastic mode. Okay, workspace. Usually, since my agent is stochastic, I also have acquisition. I have to seed this agent, so here my seed is just 0. Then what I can do is that I can show you all the variables that are in this workspace. So print k workspace of k.size. Okay, so again, I have one acquisition agent, which is an execution at each time step of the environment, then the probability agent, then the action agent, and I will just check the size of all the variables that I will have in my workspace after an execution. Let me execute this script. Yeah, sorry, I have a problem with this import. Okay, I still have a few syntax errors, as usual. Okay. Acquisition is not defined, yes, because it is acquisition agent. Okay. So it is working, and then in my workspace, what do I have? First, I have executed for 32 time steps. So all my variables, the first dimension of all my variables is 32, because the first dimension is always the number of time steps. Then the second dimension is the batch size. I am executing 4 environments simultaneously. So my second dimension is always 4. And then I have the observation, which is of size 4. I have done, which is just one value. I have reward, which is just one value. And I have my probability variable, which is 2 values. And my action, which is 1 value. So everything seems to work fine. Okay. what I want to learn is the parameters of my probe agent, but also the parameter of my critic agent. So what I can do is define one optimizer on this guy, learning rate. Okay, so now I will take the value of the learning rate from CFG. CFG is my YAML file. And I can define another optimizer for the critic agent. Okay, and then I can start my learning. So what do I have to do in my learning? First, I want to get a new trajectory. This is A2C. And second, I want to compute the loss. Okay. So first, I want to compute a new trajectory. So to compute a trajectory, I need to execute my acquisition agent over the workspace. I will execute for a particular number of steps, which is defined in my YAML file, n time steps. Okay. I want to execute this agent in stochastic mode. And then at first, I want to execute from t equal to 0. But at the second epoch, I want to execute to also capture n time steps. But if I am executing, so imagine that I am doing this acquisition agent 2 times, then what you have to see is that here I will capture all the observation from 0 to n time step minus 1, and at the second execution the environment will continue their execution, so I will capture the observation from n time step to n time step times 2 minus 1. So I mean I am computing 2 window of observation. The first window is from time 0 to n time step minus 1, and the second one will be from n time step to n time step minus 1. And if I do that, the problem in reinforcement learning is that I will lose a transition between n time step minus 1, which will be computed here, and n time step, which is the first step of this second acquisition. So I am losing a transition if I just execute the same acquisition at each epoch. So in reinforcement learning, the way we do it is that, okay, for the first epoch, we will start at t equals 0. But then from the second epoch, what we will do is copy the last time step of the workspace at the first position in the workspace. So this n time step minus 1 will be copied at the first time step of the workspace. And then I will re-execute this agent from time 1 to time 4 and for one less step. So it's just a way to such that in the second at the second acquisition step, I will keep this transition between n time step minus 1 and n time step that I would lose if I don't do this little trick. Okay, but this is the way we get we capture multiple trajectories in reinforcement learning. If you have a look at all the algorithms we provide, you will see that this is the way we are doing it. Okay, you can also use this function, for instance, if you want to compute sliding windows over the environment, you can copy here more than just one time step, but for instance 5, and then start at 5. It can allow you to capture windows over the trajectories, sliding windows over the trajectories. Okay. Anyway, here after this step, what I have in my workspace is a trajectory with observation, probabilities, action, and so on. So now what I need to do is to compute my critic because I need the critic value over this trajectory. So the way I can do it is just by executing my critic like that. Okay. Or what I can do is that I can define a temporal critic agent, and I can use this guy over the workspace from T0 to n time steps. Okay, so here I have probabilities and action, and here I will also have critic value. Okay, so this is 1 bis computing critic over the trajectory. And now I have everything I need to compute my loss function. So the first stuff I can do is, for instance, compute the entropy of the distribution. So I can get the probabilities from the workspace and just compute the entropy and the mean of the entropy. Okay. The second stuff I can do is compute the critic loss. So to compute the critic loss, I need to compute the temporal difference, and the temporal difference is workspace critic. So let me get this value into variable. So I will take the critic at t plus 1. This critic has to be multiplied by the discount factor. I have also to check if the state is a terminal state or not, because if it's a terminal state, then I don't have to use this critic value. Here I take the reward minus critic. Okay, so what I'm doing is computing critic at time t minus reward at time t plus critic at time t plus 1. Okay, and this is my temporal difference. My critic loss is just td square and that's it. Okay, and then the last loss I have to compute in A2C is the loss over the log probability of the actions that have been taken by the agent. So let me just copy paste this function. So the objective of this function is just to index one tensor regarding one other tensor. So what I do is that I can compute p action, so the probability of the action. So remember that prob is the probability of all the actions, action 0, action 1, but I want to index this tensor, so it's index, and I want to select just the value corresponding to the particular action I have taken when getting the trajectory. So p action is the probability of the action the actions taken by the agent. LP action is p action.log, and now my A2C loss is just this LP action. So I don't want to use the last action because I have no information about the last action, times td.detach because I don't want to propagate gradient over the temporal on the critic for this term. Okay. My final loss, so okay, I need also to do the mean. My final loss is, so I have three arguments, entropy, critic, and A2C coef. So it's A2C coef dot A2C loss plus CFG entropy coef dot entropy loss plus CFG critic coef critic loss. So I want to minimize the critic loss, I want to maximize the entropy. So I need to put a minus and I want to maximize this A2C loss. So now I can initialize the two optimizers I have defined previously. I can do backward and I can do a step on the optimizer. Okay, so what I can do also is print A2C loss, entropy loss, critic loss. Okay, let me test this code. Max epoch is not defined. Yes, because it is CFG dot max epoch. Ah, max epochs avec with an S. Okay. Then here I have a problem with the size of the tensors. Yes, because I have to use done from time 1 to the end. Reward is not defined. That's true. Reward is into the workspace. And then I have a backpropagation error. This is due to the fact that I am backpropagating multiple times over same variables, and this is caused by this copy. Okay, so in order to avoid this effect, I can just remove gradient from my workspace to be sure that there is no copy of the gradient that is made here. Good, it seems to work. Okay. The problem is that here I am printing the loss. So if I print the loss, I have no idea about the fact that my policy is working or not. I would like to print the reward. I can easily print the reward. So in the workspace, here I have a trajectory. So what I can do is look in the workspace to know if I have some terminal state. I can get the value of the cumulated reward, which is provided by the environment. I can select the cumulated reward of terminal state, and if I have at least one terminal state, I can print the reward. Like this, okay? So it's just a very simple way to control the reward obtained by your training policy. If you have a look at the examples we provide with the library, you will see that it's also possible to do an non-blocking evaluation of the policy in test mode while doing the training, but it is not the topic of the video. Okay. Done, sorry. Accumulated reward is not defined. Okay, yes. Sorry for that. Okay. Let me remove the print of the loss. Just print the reward, and you will see that this reward is increasing and saturating at 100. 100 is the maximum number of time steps. So what you can see that the system is able to learn to solve card-pull in a few seconds. Okay, so everything is working fine, and I have my A2C implementation. Thanks.